So good morning, everyone. So today we'll have a quick recap of capacitance. So unlike first year topic, we'll have only quick recap only. And we'll just discuss some of the points. And as we go through all these topics here, majority of you should feel that you already know it. Because this is something this we have done recently and we've done slowly. I think most of you should have revised it and you should get a feeling, oh, this I know. So let's look at this. Combination of capacitors. So in this case, what we see, these two capacitors are connected in series. What we understand in case of series, see what are the points we can understand in case of series combination. If two capacitors have a direct connection, it means the two plates of the capacitors which are connected, these two plates with the connection, they form an isolated system. So if they form an isolated system, means the net charge on the two has to be zero, and this will form an isolated system if there's no branch here. So this is a kind of series connection, direct connection between two capacitors. And since whatever charge this has, this also will have the same charge. So in case of series capacitor, charge is same on all capacitors connected in series. And when we connect to a battery here, potential is divided. So if I calculate potential difference across first capacitor and second capacitor, sum of the potential drop will be equal to extension potential drop. And which proportion and what is equivalency here in case of series, we know that formula is 1 by C equivalent equal to summation of 1 by C. And we can find equivalent capacitance here. And these two capacitors connected between X and Y point, I can replace with the equivalent capacitor. So when we replace with the equivalent capacitor, if equivalent capacitor has charge Q here, it means these two capacitors also will have the same charge as the charge on the equivalent capacitor. So if we find charge on the equivalent capacitor, we find the charge on two capacitor or multiple capacitor which are connected in series. So and second thing, charge supplied by battery. In this case, what is the charge supplied? We calculate. And how do we understand charge supplied by the battery? Ideal way to think of charge supplied by the battery is, if in this case charge supplies is 200 microcoulomb, it means so much charge has left from the positive plate. We basically, though electrons move, we talk about motion of positive charge here. So positive charge has moved from the plate. This positive charge of 200 microcoulomb has gone to this plate here, and as soon as positive charge reaches here, overall capacitor charge has to remain zero. So whatever positive charge it receives in one plate, equal positive charge leaves other plate. So as soon as charge keeps coming here, equal amount of charge keeps going out, and this will reach here. So whatever charge was reaching here, same charge will reach here also. And as soon as the charge reaches, the charge will leave this plate also, and that same charge will reach the battery. So during the whole process, the net charge transfer of the battery is zero. Whatever charge leaves, same amount of charge comes back to negative plate. A similar thing happens into capacitor. So it is equivalent to charge flow in the circuit. Only thing what happens is like a virtual charge flow. The charge flow comes here. If we ignore this part here, we can see charge flowing coming in here. And as soon as the charge comes in here, the immediate same charge is flowing out from here. So there is a continuity here, but in essence, same charge flow continues across two ends. Okay, charge on capacitor, and these are basic points we should understand here. All charge will be same, and voltage V is equal to Q by C. So we know V is proportional to 1 by C. So voltage of external 10 volts will get divided in inverse proportion of capacitance. The one with a smaller capacitance will have higher potential drop, and the higher one will have a lower potential drop. That's why I write V1. V1 will equal to C2 divided by C1 plus C2 into V, not C1, because it is inversely proportional. So we can easily find the charge also. So this will be 2 to the capacitance is 1:2, and voltage will be shared in the proportion of 2:1. Okay, so that's the ratio. And when we talk about in parallel, important point is they are connected across identical potential points here. So all three capacitors, top plates of all three capacitors are connected to potential point X here. Right from all this point, they're all part of one entire top half is like a one conductor. So everywhere on the top half potential is same. Everywhere on the bottom half potential is same. So all capacitors are connected across identical potential difference, identical potential points. They are in parallel. And this is how the charge flows. And in case of parallel, basically potential is same and the charge is distributed. So whatever that charge battery supplies, it gets distributed across different capacitors. So unlike previous case, here potential is same, charge is shared. Previous case, charge was same, potential is shared. And we come across number of questions on finding equivalent capacitance. Equivalent capacitance, this also is a kind of common question. So how do you find out equivalent capacitance? Our sequence is clear. We look for parallel combination. We look for series combination. If we don't find parallel or series combination, we try to redraw the circuit here. Because sometimes we are not able to spot. So if what is the equivalent capacitance here, I think all of you should recall. If I look at, they are not in series, not in series. Are they in parallel? They do not appear to be parallel. They are actually in parallel. How do we identify in parallel? We mark all points having connected to potential X. So this, if I mark here, see if I continue here, all these points are part of same conductor. So this all points marked in black are at potential X. All marked in pink are at potential Y. So what I notice, each of the three capacitors are connected across potential X and Y. And since they are connected across identical potential points, they are in parallel. Okay. And this become DC. And we also come across something like plates connected in parallel here. So plates also, in this case, we take a simpler case here. Each plate is of area A and spacing also is given here. And this plates also, what can happen in the plates? They may ask to find capacitance between point X and Y. So whichever point we have to find capacitance between, those 2 points, we have to assume the batteries will get connected across those 2 points. And we may also notice here, some of the plates may be connected to each other by conducting wire. So whenever these two plates are connected, potential at this plate and this plate will be equal. So let's understand how do we find equivalent capacitance when they are like parallel conducting plates. In this case, actually there are three capacitors, opposite surfaces separated by a medium. A medium could be either air or it could be a dielectric medium. So this forms capacitor. There are three capacitors here. So space between two parallel conducting surface is a capacitor. So this is C1, C2, C3. There are three capacitors connected. And in all, how many potential points? This is potential point X. This is potential point Y. These two they are not X or not Y. So we have to assign some other potential points. So again, we redraw the circuit. Each one is A epsilon naught by E. We redraw this potential point. How do we redraw this point here? So we call this point as potential P here. C1 is connected across, this is potential P point and X point. So I can draw capacitance C1 between X and P. Similarly, when I look at C2, C2 also is connected between X and P. I draw C2 also. And last one, C3 is connected between this point is P and this point is Y. And this is C3. So we can, whenever we have this kind of a combination, we can yeah, similar to this, we can mark potential point. And when these two are extreme point, whenever any point which is not extreme point, we mark those points in between the extreme points. So we mark, if there were one more potential point, I would have marked Q potential also here, and we redraw the circuit here. So I hope all of you easily recall these points here. And okay, two parallel plates. Okay. Force on the plate. So if two capacitor plates are there, and they have charge plus Q minus Q. What is the force of attraction between two plates? How do you find and how do we memorize or how do we understand this point? See, when this is the charge given here, the charge will be on the inner opposing surface. So this surface also will have charge, total charge of Q or charge density of plus sigma, and this surface will have charge density of minus sigma. These are the charge densities. And these charges are only so per charge will rearrange itself in form of two sheets. So plate A will experience force on plate A will be due to force experienced by charge on the surface here. And how do we write here? Force on plate A will be equal to charge on plate A multiplied by field. When we calculate field at the position of sheet A, we calculate the field due to charge on plate B. So field at the position of A due to charge on B. And when we calculate field here, now we are ignoring, see, it will not create a field on itself. Hence, we are calculating field only due to one sheet charge. If it is one sheet charge, the field will be equal to sigma by 2 epsilon naught. So what is the force on plate A? The total charge on plate A multiplied by field created by charge on plate B, sigma by 2 epsilon naught. So this thing can also be written as Q square by 2A epsilon naught. And this formula is not need to be no need to memorize if you understand it well. Okay. And what we note here, it doesn't depend on distance d. Even as the distance changes, the force remains constant. So when we, yes, what is the force done? Suppose we increase the separation by delta x. How much work has been done by external force to increase the separation by delta x? We need to apply an external force, which is equal and opposite to force of attraction. So when we increase the separation by delta x, work done will be equal to F external into delta x. And F external also will be equal to electrostatic force of attraction, which is equal to Q square by 2A epsilon naught into delta x. So sometimes question may come, what is the work done to increase the separation between plates or decrease the separation between plates? So this is force of attraction between two plates. Now we talk about dielectric slab. What are points we need to remember in case of dielectric slab? So you understand here, dielectric also, there's a this is something, okay, what happens in case of dielectric? Dielectric also is something like this. If you recall functioning of dielectric, it is like a dipole. So when we apply external field, dipole gets aligned, and because of alignment, the dielectric behaves as if there are two surface charge. One extra surface has negative charge, other surface has a positive charge. So effect of dielectric is what? The dielectric, there's a there's an external field created by the charge Q. External field, if it is like this, all through, this is due to charge on the plate. This is the field created external field. And because of polarization, because of dipole orientation, there's a sheet charge within the dielectric, and this field is in the opposite direction. So there's an induced field which is in the opposite direction, and net field is external field minus induced field. That's the reason net field is lesser than external field, and net field is equal to E divided by K1. What is E here? E is the field if this space was occupied by vacuum. So field due to presence of dielectric becomes 1 by K times. Field becomes lesser because of induced charge, induced field. And induced field is always in the opposite direction. Okay. So if the dielectric constants are K1, K2, K3, and they are like parallel sheets of dielectric, and their cross-section area is same as the cross-section area of the capacitor plate here. Okay. So if we have this kind of slab, what is equivalent capacitance? Okay. So let me do in another very quickly arrive at how do you arrive at capacitance, and you get an understanding also what is the basic approach for arriving at capacitance. So to calculate capacitance between these two plates here, we give a charge Q plus Q here minus Q here. And equivalent capacitance is equal to ratio of charge given Q divided by potential difference between two plates. So I need to calculate what is the potential difference between two plates here. And why would there be potential difference? Potential difference will be because of the field here. So what is the field in the first part? External field minus induced field, which is equal to, here the field is E by K1. E by K1. And so I write what is the potential difference V? V is equal to summation of E into distance. Here all the cases field is uniform. So basically what do I write here? Summation of field into distance is the potential difference. First one, E by K1, that's the field into T1. Second one, so that's a potential drop from here to here. From here to here to what is potential drop? E divided by K2, that's the field here, into T2, plus E divided by K into T3. That's the value of potential difference. And we substitute what is E here. E is the field if this space was occupied by vacuum, and field would have been sigma by epsilon naught. What is sigma? Sigma is Q by A epsilon naught. So if I substitute this value in this equation, I arrive at this expression. So whenever there are parallel plates or plates thicknesses, so T1 plus T2 plus T3 is equal to separation between plates. I can write, so A epsilon by T1 by K1, T2 by K2 plus T3 by K3. That's our equivalent capacitance. How will feel vary inside the dielectric? Just to make you understand here, if K1 is equal to 2, this is 3 and this is 4. So if these things were not there, if dielectric was not there, field would have been E. So here field will be E by 2. This will be E by 3 and this will be E by 4. So how it will be? This field was E naught in absence of dielectric medium. In this medium, for first part here, it is half of that. Second part, 1/3 of that. And third part is 1/4 of that. And why is that so? See, this, what does it mean? Why it has become half? Because if this field is E, induced field also is equal to E by 2. That's why resultant field has become half. This has become 1/3. This field is 1/3 because induced field is 2/3 of external field. And why this field has become 1/4 resultant? Because E is the field, because the charge Q, this is equal to 3E by 4. And why 3E by 4? Induced charge is 3/4 of the charge Q. Here the induced charge on the two surfaces is 2/3 of Q. Here induced charge is Q by 2. So see that all parts of this is understood. This example explains behavior of dielectric medium. And even conductor also. What is value of K for a conductor? For dielectric, K is equal to infinity. So what does it mean? K is equal to infinity means the field inside. See, if the conductor was not placed here, the field would have been E here. But in this case, inside the conductor, field is E by K. So what has to be the case so that field becomes 0? K has to be infinity. And how do we get value of K? If field inside the conductor is 0, it implies dielectric constant for conductor is infinity. And why is dielectric constant infinity? Because induced field is equal to external field. So if this charge here is plus sigma here, the charge induced on this surface will equal to minus sigma. So induced charge in case of conductor are same as these charges here. So it completely nullifies the field created by external charge. So K is infinity. So if I place a conductor in between the plates of capacitor, and how I place the conductor? I place at a distance of T1 from the positive plate, at a distance of T3 from the negative plate, and thickness of conductor is T2. What would be equivalent capacitance of this system? You can still use the same formula. Only thing what I'll do here, for T1, this is still air medium. So K1 is equal to 1, K2 is infinity, and K3 also is equal to 1. So if I substitute this value, this term becomes 0. It becomes A epsilon by T1 plus T2. And T1 plus T2 is nothing but, if I take this thickness as T, is A epsilon by D minus T. So effectively, if thickness of conducting plate is T, it doesn't matter where I place this conducting plate. So it doesn't depend on T1 and T2. Effectively, earlier the spacing was D. It effectively reduces the spacing between plate by distance equal to its own thickness. Effectively reduce the spacing by amount equivalent to its thickness. Its position does not affect the capacitance. Anywhere, if I make it, place it in contact with this conducting plate. So what is the effect of if I place it in contact with this plate here? The spacing gets reduced here. That's all. It doesn't matter where I place it. And how would field vary here? In this case, field here, this space field will be E naught only. In conductor, field becomes 0. And again, it becomes E naught here. So what will the potential difference? Potential difference will be E naught into T1 plus E naught into T3. That will be the potential difference. Then we come across case of insertion of dielectric. So when we should understand here, and this battery here, There's a capacitor here, and we understand one point we should easily understand is whenever we insert a dielectric medium here, if we insert a dielectric completely between the plates of the capacitor, this capacitance becomes K times, if K is the dielectric constant here. So let's examine two cases here. So there's a capacitor. There are two ways we can insert dielectric. One case when battery is connected and dielectric is inserted and it occupies full space. Second case, battery is not connected. After charging, the battery is disconnected and then dielectric is inserted. So let's do one by one. And what is important to understand, moment we say the battery remains connected, it means two plates of capacitor have same potential as potential of the plates of the battery. So they will have same potential difference as the battery potential difference. V will remain constant. And if battery is disconnected, it means they cannot receive or give away any charge. Charge will remain constant. So when battery disconnected, charge remains constant. When battery remains connected, potential remains constant. Okay, let's do that part here. First case, let's do when battery is connected. So this is battery connected, and now we inserted a dielectric K. So what are things? What are the parameters which are important here? These are the five parameters, and let's put one by one. Which are the easiest to substitute here? See, moment we insert a dielectric, it doesn't matter connected or not connected. Capacitance becomes K time. So this is I can easily fill it up. Capacitance becomes C time. What else I can substitute here? Other thing I substitute, since battery is connected, potential will be same as battery potential V. So I have V value and C value. Once I have V value and C value, I can find charge. Charge is equal to CB. I get this is the charge. So charge has become earlier when battery was not when before it was inserted, the charge on the capacitor was CB. After this dielectric is inserted, its capacitance has increased, hence more charge has flown into the capacitor. How much extra charge? Earlier it was CV, now it becomes KCB. So more charge will be supplied by the battery when it is connected. And reason also simple. See what happens here. Earlier the field was E, distance was D, E into D was equal to V. Even after dielectric inserted, if potential difference remains same, you need same field. But to have same field, the charge has to be Q times more. Then only field remains same. The field has to remain same. So now I come to field part. Since the potential difference is same, field is equal to potential difference by spacing here V by D. The field has remained same. And how about energy? Energy we can write in three form: Q square by 2C or 1 by 2 CV square. So before it was inserted, this was the energy. Voltage has remained changed. Charge has become K times. Energy also become K times more. KU. Second case, battery is disconnected after charging. So we have given charge to capacitor. So capacitor has charge. This plate will have charge plus CV. This here will have minus CV. If battery is not connected, it means charge remains same. Can we fill up all the parameters here? Should be easy. Let's put one by one, which are the easiest one to put here. Of course, this will always be KC. Second thing, since the battery is disconnected, charge will remain same. I can connect, yes, this is equal to CV. And once I have charge and capacitance, I can find out potential difference. Potential difference has become V by K. How do we understand why it has become V by K? Charge has remained same. If charge has remained same, the field has become E by K. If field has become 1 by K times of initial field, potential difference also become V by K. So this was the potential difference before dielectric was inserted. And we can find field. Field has remained. Field has become V by, earlier it was V by D, now it has become V by D. And energy. Energy also, let's look at this term here. We can use term Q square by 2C here. Energy is Q square by 2C because why I'm using Q? This remains same here. Capacitance has increased by factor of K. Hence, overall energy has decreased by factor of K. And where that energy has gone, so if this energy, if we bring this slab here just to the edge of the plates here, and as soon as we bring the slab here and leave it, it will be pulled in by force of attraction here, and it will acquire a kinetic energy. And actually, if we leave the slab here, because of force of attraction, it will keep oscillating. So this energy, either if we hold it by our hand, you will feel we have to do negative work to counteract the force of attraction. So negative work has to be done by external agent to place it slowly. Or if I release it, this energy, loss of energy, will go in form of kinetic energy. Okay. Now, earlier we had taken when the full space was occupied, or we can also do some cases, two dielectric slab, each occupying half the cross-section area. So always imagine this is the ceiling of the capacitor, and this is the floor of the capacitor, and we see from one side. So what we say, in this case here, it is occupying the full height of the room, but it is occupying the half the floor area, half the ceiling area. So you should understand what does it mean here. So this one, it has full depth here. So thickness of dielectric slab is equal to spacing between capacitor plates, but area of cross section is half. In this case, if I insert a dielectric K1 here and this is K2 here, what is the equivalent capacitance between plates X and Y? This is a conducting plate, top is a conducting plate, full, and bottom is a conducting plate. How do I find in this case? I treat left part as one capacitor, right part as another capacitor. And since this point potential is same as this potential, both are connected to potential X, bottom is connected to potential Y. They are connected to equal potential. So two capacitors connected in parallel. So this is how, even though they are seen to be together, mentally I can separate them. I can represent them like this. And I can calculate capacitance of this. This capacitance will be equal to is capacitance in vacuum multiplied by K1 times, is capacitance in vacuum multiplied by K2 times, and then C1 plus C2. So very simple, connected in parallel. C1 will be equal to area is A by 2 epsilon naught divided by D into K1. Similarly, calculate C2 and add it up. That's the capacitance. Another point I would like to make here, if we connect it to battery and the battery supplies some charge here, so will the charge be, if the total charge which is gone is Q, will the charge be equally shared between two half of the plate, the same conducting plate? So will the charge be equally shared? No, it will not be equally shared. Because here it is just imagine it is something like this. If I connect a battery here, will the charge be equally shared between two capacitors? No, the capacitors are connected in parallel. And when they charge the Q is equal to CV, for same potential, charge is proportional to capacitance. The one which has higher capacitance will have more charge, one which has lower capacitance will have lower charge. So charge will not be equally shared, and charge density here sigma 1 and sigma 2 will not be equal. Okay, so the charge will be such that field has to be equal. So whatever field is there here, if this has field E1, this also has to have same field, then only potential difference is same. So these are the additional points we can understand and keep in mind. Coming to if there are three slabs. So again, think of this. This is the ceiling of the room. This is the floor of the room. In one half the room, this occupies the full height and half the area. And this side, half the area for half the height, one slab, other remaining height, other slab. If it is like this, how do you find equivalent capacitance? This also becomes something like this. Again, I divide into two parts. These parts and these two are in like a series combination. While there's a series combination, they have the same charge. If whatever charge, if the charge goes here is Q2, all of them, both of the charge is Q2. We are not ignoring the induced charge here. So charge, both will have the same charge. They are in series. So this is series combination. This is parallel. And we find out equivalent capacitance of these two first. And after finding equivalent, they are in parallel. So what is the equivalent capacitance? C1 plus equivalent capacitance of C2, C3. And C2, C3, C2 into C3, and C1, C2 plus C3. We can find those values. So if we have to find equivalent capacitance of this system here, if something like this is given, can we find equivalent capacitance? No, because equivalent capacitance we always need to define between which points. So if a point is defined, then only you can find equivalent capacitance. Okay, so if we find equivalent, find equivalent capacitance. If two of them are connected here, what is important point to understand here? Total applied voltage is 9. V is equal to Q by C. The voltage will be shared in inverse proportion of capacitance. So this will have 2/3 share. This will have this will have 2/3 share. This will have 1/3 share. So this from here to here potential. If I call this potential as zero potential, this will have zero potential. This will have potential of 3 volts, and this will have 6 volts. So we understand this one. Potential gets divided like this. Let me take if I connect one more combination in parallel. So does charge distribution in this gets affected because this also has been connected? No, this does not affect this and this does not affect this. As far as these two combinations are concerned, both are connected across battery of 9 volts. So parallel combination, they are independent of each other. Only thing what will happen now, battery has to supply charge for this system of capacitor as well as this system of capacitor. What I notice here, this also is similar ratio. So this point will have 3 volts potential. This point will have 0 volt potential and this has 6 volt potential. So any combination where this ratio of capacitance and this ratio are same, potential at this point will be equal for whatever the values of this and whatever the value of battery. So if I connect a capacitor across these 2 points, it will always have equal potential. If potentials are equal, it will never have any charge. And this is nothing but Wheatstone arrangement. The key point here, I can remove this capacitor here. So whenever we have combination of 5 capacitors, we can check whether it forms a Wheatstone bridge. If it forms a Wheatstone bridge, we can remove one which is connected across like this. So this capacitor can be removed. So equivalent capacitance of this is same as this. Another combination comes in if we have 2 capacitors. Initially, what we do, we charge one capacitor. And suppose this is 10 microfarad capacitor, we connect it to a battery of potential 500 volts. It acquires a charge of 5 millicoulomb. This is a capacitor. This another capacitor. We take the case first when this is not charged here. If this is uncharged capacitor and we connect them together, so we connect either 2 capacitors of unequal charge or any two other. So first we are taking when there's no charge. When we connect them, what will happen here? Now, once they are connected, two things. If I call this point as X potential and this point as Y potential, entire top half will have same potential, bottom half will have same potential. So they will become equivalent to 2 capacitors connected in parallel. So whichever way it is connected, any 2 capacitors if ends are connected, they always form a parallel combination. And second thing, since when there's a positive charge here, this some charge will redistribute, charge will flow into this also. So it will become something like this. So the whole thing will become equal to 50 microfarad capacitor parallel combination. So whole system is equivalent to now top plate will have a charge of 5 microcoulomb. So earlier 5 millicoulomb charge was on 10 microfarad capacitor. If we connect these two with the wire, it becomes capacitance increases, charge remains same, potential difference will change. And V will change and there will be loss of energy also. So can we find what is the new voltage? Earlier it was connected to 500 voltage when charge was 5 microcoulomb. Now from 10 microfarad it has become 50 microfarad. C has become 5 times. The voltage will become 1 by 5 times. This voltage will be equal to 100 volts. So from here, this also will have 100 volts potential difference. This also will have 100 volts potential difference. If this is 100 volts, this will have 4 millicoulomb charge and this will have 1 millicoulomb charge. So this 5 millicoulomb charge will get distributed between 2 capacitors in inverse proportion of their capacitance. So can we calculate loss of energy? This part had initial energy and combined capacitor is the final energy. So can I easily calculate here? I don't have to add it up. I can calculate energy on the equivalent capacitance also. The energy in this capacitance will be equal to energy in this plus this with these charges here. So easily I can calculate charge is given Q square by 2C is the initial energy here. In earlier C equivalent is 50. Some if the charges are connected. Initial energy can be calculated 1 by 2 CV square. Final energy can be calculated Q square, whichever we can calculate. And you'll always find this energy will become lesser. And where would this energy go? This energy go when we connect across the wire. Even we say it is a very low resistance wire, it will have some resistance and heat loss will take place. So this loss of energy is in form of heating effect in the connecting or lead wires. Dinesh?
So I don't understand why charge should be shared in inverse proportion in this case.
Wire charges in shared inverse proportion. Okay. When we connect like this, will the potential between this plate and this plate and this plate will be equal or unequal?
Yes, it will be equal.
Equal. Why?
Like they connected across, like with the
No, no,
same wire.
same wire. So this whatever top one, if potential difference are equal, so I have two capacitor. V is equal for both of them. What is V equal to? V equal to. So if there are they not like parallel capacitors? If they're parallel capacitor, how is the charge shared in case of parallel capacitor?
Direct proportion.
Yeah, sorry, but what did I say? I said inverse proportion. Eh? Okay. Yeah, the charge is shared in direct proportion. Voltage is in inverse proportion. That's one mistake I made. Okay. So charge is shared in direct proportion. Charge is shared in direct proportion. That's why this is 1 microcoulomb, this is 4 microcoulomb. This is 10 and this is 40. So this is 1 and this is 4. Yeah. I think my wording. So I use inverse proportion. Eh? So direct proportion. Now coming to this kind of question. And this also capacitors initially uncharged and connected to diagram with switch open. So when we connect them together, and let's say if we connect a battery also, VAB is 360 volts here. So if we have a battery here, or we can also show like this. Sometimes we show what is like this. We write as 360 volts this point. And if I show something like this, other point is connected to earth. This also is equal to potential difference of 360 volts. So if we have this kind of arrangement, when switch is open, these two are in series, these two are also in series. And if they are in series, what is the equivalent capacitance here? Equivalent capacitance 6 into 3 divided by 9, that is equal to 2. So equivalent capacitance is 2, voltage is 360. So charge will be equal to 720 microcoulomb each one of them. Okay. And what will the potential at point D? So when they are connected like this, can we calculate potential at point C and D? You can easily calculate potential at point C and D. What are the way you can calculate? Two different ways you can calculate. First, we can find out charge and then calculate V is equal to Q by C, or total potential difference of 360. Potential gets divided in inverse proportion of capacitance. Where the potential drop will be more, here potential drop will be two proportions here and one proportions here. So if you divide in total three parts here, 120, 120, one part here, 120 volts, and this will be 240 volts. Okay, so if this is 0, this potential will be equal to, this point is at 120 volts. Similarly, if I go to the lower part here, this part again, this part will be equal to 120 volts and this will be equal to 120 volts across this capacitor, and this will be equal to 240 volts. Hence, potential at this point will be equal to 240 volts. So that's first part. If switch is open, which point has higher potential? What is potential difference between C and D? VC minus VD. VC minus VD is 120 volts. Okay, that we can easily calculate. So we understood. So what will happen? Potential difference are equal, but this is 240 and this is 120. And what is the total charge contained in the two capacitor? This is what the charges are. And if I have to mark charge distribution, this will be equal to plus 720 minus 720 plus 720 minus 720. Same way in the bottom also. So just keep in mind this is how the charge distribution, voltage share, and these are and potential different points are. What happens if I close the switch? If we close the switch here, this basically means earlier this was 240 and this was 120. Now once we saw Yes, they have to become at equal potential. So we can understand in another way also. Earlier, these two capacitors were in series. These two were in series. Moment I close the switch, these two become parallel. These two become parallel. Whole arrangement changes. Equivalent capacitance changes. Charge distribution changes. So let's read previous case. Top half was 2 microfarad. Bottom was a 2 microfarad. So initially, C equivalent was equal to. Now what will the value here? Is the capacitance changed here? Let's look at this. If we connect also when it's connected like this is parallel combination, this is parallel combination. So this one is 9 microfarad, this also is 9. So what is new C dash? 9 and 9 connected in series, it is equal to 4.5 microfarad. So capacitance also has changed. So total charge distribution also will change. Okay. Can we write charge distribution as well? How much will be the charge distribution here? So 340 volts, they are connected in parallel, and this will be this is 9 and this is 9. So this will be equal to what is the potential difference from here to here? 180 volts. And if I have to find how much is the charge flow, what I need to do to find the charge flow? The charge flow, what I need to find here, see, we had done earlier these two plates were forming an isolated system. Net charge was 0. Now, if I check the net charge on these two top plates, if net charge is not 0, what does it mean? Why it is not 0? Because it has some charge has entered into this system or left the system here. So charge flow across the switch. So either I can calculate net charge on this system or I can calculate net charge on this system. There's some transfer of charge from this part to this part. So if this net charge is plus Q, this will be equal to minus Q of that nature. So to find charge flow, I need to find sum of charge in these two plates. So I need to find charge of this capacitor and this capacitor. Hence, one way of finding, I found the potential difference is 180. If 180, this charge will be equal to plus 540 minus 540. So, and what will be the charge here? 180 is potential difference. This will be, this is the charge. Charge is equal to C into V. So what we find here, what is the net charge of the system? Now the net charge on this system is not 0. And you can understand the reason also, it need not necessarily be 0. We find charge on this system is equal to 550 microcoulomb. Where from this 550 microcoulomb has come? That has flown in from the switch. And the reason it has flown in, why the charge flow has taken in this direction, can someone think and tell? Why the charge has moved from C to D after we close the switch? Could we have predicted the charge will flow from C to D? Because before the switch was closed, C was at a higher potential and D was at a lower potential. So charge will flow from higher to lower potential until the potential difference becomes 0 here. So this is the charge flow after closing the switch. So we can then calculate that as well. Okay. Go through the next question. And this also is past question. They're fairly simple question. Just all of you read that one, see that you can easily understand what we need to do in this question. So C1 is charged by 60 volts battery. So we can easily understand how much charge it will have. It will have a charge equal to plus 60 microcoulomb by connecting the battery. So switch 1. Now C1 is disconnected from battery and connected to circuit consisting of two uncharged capacitors C2 and C3. This is 3 and this is 6. So conceptually, I can take this as one capacitor, and this one capacitor is equivalent to 2 microfarad. So it is connected like this, and we have done such question. So it is a case of one capacitor having certain charge connected to other capacitor like this. When they connect together, what happens? They become in parallel. So before the connection was made, whatever charge was there, charge remained constant. Capacitance changes. So when we connect like this, what is the point? Net charge remains same. So what will be the net charge on the system? So when we connect like this, C1 and 2, these two will become in parallel. So C equivalent will be equal to what? In this case, after they are connected together, the charge Q will remain same. Charge Q will remain equal to plus 60 microcoulomb. It's isolated system. And what will be C equivalent now? This is 2 microfarad, and this is and what is this one? This is 1. So 1 plus 2 connected in parallel, this is equal to 3 microfarad. Okay. The sum of charge on C2 and C3. What is the charge we have to calculate here? Okay. How do I calculate the charge? There is a number of ways I could have calculated. One way of calculation would be the total charge is 60 microcoulomb. It is getting distributed in two parts. This part is 1 microfarad and this one is 2 microfarad. So the charge will get distributed in 1 to 2 proportion. Q is CV. So the 1 to 2 proportion means what? Total 3 proportion. 1 goes here, 2 goes here. This will have plus 20 microcoulomb and this will have 40 microcoulomb. This is charge distribution. Or other way, if the question was find the potential, and since they are connected in series, whatever charge equivalent capacitor has, same charge will be there on both the capacitors. I have found charge on equivalent of C to C3. But whatever charge there in the equivalent capacitor, same charge is there on two capacitors connected in series. So number of ways you can find out. And if we have to calculate loss of energy also will be calculated. Initial energy and minus final energy. Some more question or something like this. We have done parallel plate capacitor. What if plates are not parallel? And this question can also be given like this. If top plate is making an angle alpha with the horizontal, and if this is a dimension given, what is the capacitance of the system? How would I calculate capacitance of the system here? Our formula is, we using the formula, we know C is equal to A epsilon naught by D. A is the area of the plate and D is the separation. Here separation is not uniform. What we can do, we can, if we take divide into small pieces here, if I take a small part of a capacitor, which part, if I take a slice like this, so I divide into several slices and take one slice like this. If I take for the small slice here, the distance separation can be taken as constant here. So I divide the whole capacitor into several parallel capacitors. So I calculate the capacitance of one piece and add it up. So what is capacitance of this part alone? This part alone is width B and area. Area is equal to, this is dx into B becomes area. This is area term into epsilon naught. And the distance d here. The distance d will equal to y naught and plus extra this height here. What will the delta y? Delta y by x is equal to tan alpha, or delta y is equal to x tan alpha. So total d will become equal to y naught plus x into tan alpha. That is DCE. Total capacitance is integration of this, which you should obtain. A similar question like this, if the space between plates of a parallel plate capacitor is filled with the dielectric, so it is like two triangular prism here. So diagonal is filled like this, one is K1 and one is K2. So in this case also, again, we divide into several parallel pieces and we calculate for DCX here and add it up. What is DCEX here? So this also, when we calculate here, this piece also has two dielectric mediums. And when we had two dielectric mediums, what is equivalent capacitance? When the two of them, they are of thickness is shared between the two of them, it is equal to A epsilon naught divided by D1 by K1 plus D2 by K2. So I'll use that formula. I'll just calculate D1 here. So I have taken a slice at a distance x from the left hand of thickness dx. So this height T1 will be equal to d divided by L into x. So even if area is not given, so I'll assume this length to be L here and width also to be L, so that L square is area. So I can calculate dx by K2L, and similar to other one also. Okay, so T1 by K1 and D minus T1 by K2. So I can calculate both of them and you can solve. The question all of you read and try and figure out how you solve. So my throat is almost gone. So just read the question here. So area of the plates of parallel plate capacitor is A. Gap between them is D here. And plates of the capacitor are parallel to XZ plane. And so this direction is Y direction. Lower plate is at Y is equal to 0. And gap is filled with non-homogeneous dielectric. So it is like infinite number of, so it is like several thin layers of dielectric. Each layer having a different dielectric constant. Okay, because dielectric constant is varying as y as a function. We need to assume infinite layer of dielectric thicknesses, and it is this entire capacitor is equivalent to infinite number of capacitors connected in series. So I'll calculate capacitance of one random capacitor and add it up for series combination. How do we do it? Let's look at that. Combination when we have series combination, we don't directly add capacitance to obtain equivalent series combination inverse. We take summation of 1 by DC. So we'll calculate capacitance of one random slice. What is the random slice? Random slice is at a height y from the base of thickness dy. So what is capacitance? Area is A. So area is A into epsilon naught into K term here. What is value of dielectric constant? This is dielectric constant here. So I entered this dielectric constant here. Divided by is thickness. Thickness is dy. So this becomes 1 by dc. If I add up all 1 by dc, I add up all inverse value of capacitance by integration from 0 to d. Take a chapter. So we add it up through integration, and it's a very simple integration. All of can easily obtain. Okay. So just stop here, and I'll just take a break, and again we meet up at 11:30.